Hello and welcome to another tutorial in ANSYS Workbench. In this tutorial we're going to take a simple structure, truss, with one horizontal member here and a diagonal member. These two pin joints are connected to the wall, and we have one transverse load of 2,000 newtons applied here at the end of the beam. This R load is the reaction generated by this diagonal member to hold the system up when the 2,000 Newton load is applied. So in this tutorial we're going to focus on two main concepts. First, we will learn how to create a pin joint in a truss member, and we will also look at buckling. And so this will be a linear buckling problem where we look at the buckling load required to have this diagonal member here buckle. So I hope you enjoy the video. The geometry for this model is relatively simple to create. So after opening Space Claim, I'll close the dialog window. I like to change my sketch plane, so I right click, select new sketch plane, click on the XY plane and click Plan View. The default units in Space Claim are millimeters. I want to use meters, so I'll go to File, left click Space Claim Options, and then when the dialog comes up I'll click Units, and I will click the drop down to select meters. Then I can scroll down and change the minor grid spacing to 1/10 of a meter and click enter. Now I'm ready to go ahead and begin building the geometry. So I'm in sketch mode. I can come to the line and click on the line. I'll start at the center, so I left click the starting point, drag this over here, and this is to be 1.5 meters. Now I have another line out here that will be 0.5 meters. Now I'll hit escape, come find this point here, and you need to make sure you find the end of the beam or the joint between the two beams. I'll click on that point, bring it over to the wall, and that should be a 30-degree angle when you're at the wall. So I have 30 degrees there. My line is 1.73, and I can go ahead and click to finish that line. Then I hit escape twice and I'm out of the line mode. I need to go up and create a cross section for these beams, so I'll come up to prepare, left click on profiles. I'm going to just do a solid circular cross section of 0.06 meters. So I'll click, then come over and open up the beam profiles. I will right click on circle and left click edit beam profile. Now I need to make sure that I remember I'm entering the radius here. So I'll click on ruler dimensions, click on the blue number to change it to 0.06 meters. And I just made a mistake there, so I'll come up and undo that, and I'll come back to ruler dimensions and remember that I'm entering a radius value, and I'll go 0.03, enter. So I now have my cross section built. I can come back down here and get out of the SYS window, open up my design window again, and come over in my groups and switch to the structure tree, and I can see that I have my beam profiles and my curves. So I need to take these curves and turn them into beams, and to do that I will click the top line and shift click the bottom line to select them all, and then come over and click on create, and that has just created beams. So I don't have any more curves over here, I have just straight beams. Now what I want to do is I want to combine the first two beams into one solid beam. So to do that, I will click on the top, and you can see how you can't click and hold it, so you need to come back to design and then select and design, select, and now you can click on the top and then control click the next line, right click and move to new component. This is default component number 1, which is fine for now, but I'm going to select on that and come down and change the share topology from none to merge. So now I have these top two members here have been merged together, and I have my other member down here which has not been merged. So that is my geometry. I'm ready to go ahead and open ANSYS Mechanical. So after opening ANSYS Mechanical, I can see that my geometry has been brought in. To look at it in the XY plane, I can just click on the Z arrow, and it looks good there. Graphically, I can come over and I can see my top beam and my bottom. I'm actually going to change the name on that, so I'll click it, then right click, rename, and I'm going to call this beam 1. Then I will right click on this beam member, rename, and I'm going to call this simply beam 2. Now I can go ahead and close the geometry. My cross section has been brought in as a circle, which is great. On coordinate systems, I need to insert a reference coordinate system. So I will right click on coordinate systems, insert coordinate system, and now I need to click the geometry as to where to put that. So I'm going to come over here and select vertex selector, click on it, come down and click change, and you can see that origin now has been set at 1.5 meters and 0, 0. I do that so that I can put a revolute joint there, or a pin joint. So the other defaults here are fine, the x-axis and the y-axis, so I'm good to go ahead and close the coordinate system. Now I need to work on connections, so I will right click, insert, and I'm going to insert a joint. So I insert joint, and now the kind of joint that I want to insert, I click on type, open the drop down, and I'm going to insert a general joint. So I'll click on general in the drop down, and now I need to come and pick the members where the joint will occur, and those members are going to be the vertex on this top line and the vertex on this beam number 2. So I'll come over here and click on selection. Now I'll go use the vertex selector again and click that point, and I can see down here that it has my first line highlighted, so that's the line that has been selected, and I can simply click apply. When I roll back down here, it says I have one vertex selected on beam number 1. Now I need to click the vertex on the second beam, so I come up and click, and now I need to come down here and click on the second plate, which means I'll be clicking on beam number 2. I come to the scope, click apply, and now I can see that I have selected one vertex on beam number 2. I need to come up and change or define the degrees of freedom at this joint, and in this particular joint I want X, Y, and Z fixed, but I don't want all my rotations fixed. I want this to be able to rotate freely about the Z axis. So I will click on Fix All, click the drop down, and click on Free Z. Now my joint has been, my pin joint out there between my two beams has been created, and I can go ahead and close. I'm ready to hit mesh, so I right click, generate mesh. That mesh looks fine. I'll go ahead and use the default mesh as the actual mesh that I use to solve the problem. So I will right click on static structural, insert, and I'm going to insert a displacement, and I'm going to insert a displacement on this top node. So I click it, click apply, and now I want all of these degrees of freedom to be 0, so I click on them and enter a 0. Right click on static structural, insert fixed rotation, click on the joint, click apply, and now I want all of these fixed except the rotation about the z-axis I want to be free. Now I come down and set those same boundary conditions on this lower joint. So I will come to right click static structural, insert, click on displacement, click the point, click apply, and set all of these to 0 by clicking and entering a 0. Right click on static structural, insert, drop down to fixed rotation, and again click the point, click apply, and free the rotation about the z-axis. So I now have my boundary conditions applied here. If I click on static structural, I see all of them. Now I need to add my load out here on this point, so I will right click static structural, insert, go up to force, click the point, click apply. I'm going to enter this by component, so I left click on defined by and left click again to bring up the tree or the drop down, and I click on components. There will be a Y component of 2000 newtons, so I'll put in a minus 2000 so that the force is going downwards. Now I have my force applied, and I can click on static structural. I have my force, I have my boundary conditions, and I have my joint created. So I'm ready to go ahead and look at the output that I want. So I will right click on solution, insert, deformation. I want the total deformation. Right click again, insert, beam tool, and this will give me the direct stress, minimum combined and maximum combined. Those will be good enough for now, and I will go ahead and do a static solution. So I will right click on solution, click solve, and while this is solving, I'll do a quick pause. So my solution has been obtained, my model has been solved. I can look at the total deformation, and this deformation seems to make sense. My point out here on the end of my truss is the largest deformation. I can rotate it around, and there has been very little deformation here, essentially 0 in that diagonal member, and I have some deformation in this top member. If I look at the stresses, I can see that my direct stress here, this member is uniform, constant value, a constant value after my joint, and my member down here is a constant direct stress value. When I click on maximum combined stress, this also makes sense that this beam here did not change in magnitude from the direct stress, and that's because it has pin joints, and under pin joints there should be no bending moment, and so the stress, the maximum combined stress, would be the same magnitude as the direct stress. If I want to increase the displacements and how they're seen, I can come to result and click the drop down and click, and I can see the displacements in my truss system. So everything looks good here in my static model. I'm ready to go ahead and do the buckling portion of this. To do this, I will minimize the ANSYS mechanical window. I come back to the main project window and I go up to Eigenvalue buckling, and I click on Eigenvalue buckling, bring it over and scroll down to model and release the left mouse button on model, and this will bring up a buckling drop down or a buckling tree. You can see that the engineering data, the geometry, and the model, including the static analysis, has been brought over into the Eigenvalue buckling module. I need to also bring in the static structural solution, and so to do that I click on solution and drag that over to setup and let go, and now I have connected the solution to the setup in my Eigenvalue buckling problem. Now when I come back to double click on model and bring up mechanical again, when I scroll down to the bottom, you can see that Eigenvalue buckling has been added to the tree, my structure tree, and I'm ready to start to look at any buckling situation that I need. So to do a buckling analysis, you can see that first of all you need to do this static analysis. I have lightning bolts here, so I need to go ahead and update that, and so I will right click on solution and click solve again. Again, while this is solving, I will pause. So after the model has been solved, I can come in and look at the direct stresses again and the maximum combined stress. All that's been done is another static analysis. I'm ready to go and look at a buckling problem. I can right click on Eigenvalue buckling and insert, and I could insert any of these items here. For this buckling problem I don't need to do any of that, so I'll continue on down the structure tree. You don't really need to do much in the pre-stress, as the pre-stress was done up here in the solution. On analysis settings, you often want to increase or change the maximum modes, the buckling modes. The default here is 2. I want to increase this to 5. So I'm going to solve for the first 5 buckling modes of this problem. On the solver, since this is a beam model and very simple, I'm going to go ahead and click the drop down and do a direct solver type. You can come here and change output controls if you want and look at different values. I'm going to go ahead and just use the defaults. Now in terms of solution, I need to list the outputs that I would like, so I will right click on solution, insert, and do a deformation, a total deformation, and then I will right click and insert another total deformation, and that will be for the other mode. Insert deformation total, one more or two more, insert deformation total, right click, left click insert, left click deformation, left click total. Now I can come back up here on the first total deformation. It's looking at mode number 1. On the second total deformation, I want to click the drop down and increase that to 2. My third deformation, I want to increase that to 3 and then increase to 4, and my last one I want to increase to 5. So now I have all my total deformations put in, and this is where I will get my buckling load values. The buckling load will be shown by this load multiplier. So now I can come again and come up and right click on solution and click on solve, and again while this solves I'll go ahead and pause. Now my solution has been obtained. I can look at these total deformation values and look at the buckling mode. So in this first case, the first buckling mode of this truss member is seen by the wavy line there in the top member. The second one you can see is another mode of buckling. My third deformation is another buckling of the top member, and finally my fourth one is the buckling mode that I'm interested in determining, and you can see it's the buckling of this diagonal member here. The load multiplier is 78.147, so that needs to be multiplied by the load that is in this member right now to get the buckling load of that member. To do that, you can scroll back up to solution, right click, insert beam results, and click on axial force, then right click on axial force and left click evaluate all results. Now you can come and click on the axial force, and I can see that the axial force in this diagonal member is 5,333.3 in compression. So to obtain the buckling load, I need to take this 5,333.3 and multiply it by this load factor of 78.147. Going back to my page on hand calculations, here I computed the critical buckling load by hand, and I entered in all the various values for this truss member, and I get 4.18 e to the 5. Now when I come down and take my ANSYS results, which is the 78.147, my load magnification, multiplied by my load of 5,333, I get 4.167 e to the 5. So these two values are very close to each other, and it has been shown that ANSYS computed nearly the same value as the hand calculations. So I hope you've enjoyed this video. Thank you for watching.